So this is the project for modeling a multiprocessor MP system with MESI cache coherence for parallel dot product computation, made by Saul Gomez Ramirez and Kevin Rodriguez Lanusa. So a brief introduction. Our project simulates how several processors can work together on the same task, just like a team dividing work. We wanted to see how they communicate and keep their data consistent, which is a key challenge in modern computers. The goal, see how they share information correctly. Our focus is speed, organization, and consistency. So for that, basically, we built a small virtual computer with several processors working as a team, right? And well, motivation, why we did this project. Basically, every device today has multiple processors working at the same time, but if two of them try to use or change the same data, errors can happen. So our goal was to simulate how processors avoid those mistakes and keep everything working smoothly. So this helps explain what happens behind the scenes inside a CPU. Keeping data consistent. Imagine like four people solving a big puzzle. Each takes a corner, but if they move the same piece at the same time, it won't fit at all. So processors face the same problem when they share memory, so they need to clear rules to cooperate, right? So we used a method called MESI to keep data organized. Each piece of information can be new and updated from the letter M, only used here that it means exclusive, shared with others from the same word shared, and no longer valid. So from the word I that begins with invalid. So basically, the system avoids two processors changing the same data at once. We can see how the puzzle works here in this picture, which is kind of messy. But well, we just explained this briefly and overview it. Now we're going to see how the real system was built.
Well, now let's see quickly the results, a little bit of our results. And the figure shows the final state of each cache line on every processing core. States are from the MESI protocol. Exclusive means a core has the line only to itself. Share means multiple cores read it. And modify means a core change it locally. But saying exclusive for most lines tell us reads were local and conflict-free. Finding a shared line shows correct sharing for read-only data. The modify line confirms the protocol allow the save, write, and keep other copies invalidate. So these results show us that the behavior of the MESI protocol was already right. The next slide, where we find the final flaws and correct results. Here we have a proof and evidence that something really simple. The processing elements did the right arithmetic operations, and they gave us the right results. And then when we flush the caches before reading the results, that led us to have the the right results from the cache to the principal memory. So that led us to say that we have a correct behavior, the right behavior of the project, where we can find the dot product match with the expected, what is amazing. In the next one, we can see the write misses and boost rdx. Here a core tries to write but does not have the line. It issues a boost rdx request to gain exclusive access. After the boost grants exclusively, it writes in its cache. This sequence prevents two cores from writing the same data at the same time. That's the part that it's important for us. Did prove that we have the right data in the space we expect to have it. The boss measures total give an overhead measure. The metrics let us quantify the communication cost of maintaining coherence and form a baseline for the future tuning. This evidence show us that right behavior of the project and the expected behavior, showing us the communication between caches and the principal memory and between the processing elements was the expected in the results, in the behavior, and all we did for this project.
This presentation, we have three conclusions. First one, correct operation. The system produced the expected results, confirm accurate data processing and communication. efficient parallel work, each processor completed its task independently, showing effective collaboration without conflicts. And balanced communication, message exchange was consistent and minimal, providing efficient resource use and scalability potential. So that's how we understand um, how CPUs work behind the scenes when it comes to data ordering and retrieving. Thank you very much.